Okay, so just now we have seen that transformation of your delta source to equivalent your what you call this equivalent to your star source, right. So I showed you that how one can do it. So this is actually this is your what you call, if it is your VAB, VBC, VCA, you form the delta. I told you, right, that VBC, so this direction, and VCA this direction, then you make equivalent star, and this point you mark as AN, right. And accordingly I showed you that how the relationships are, right. So now, so this is all this relationship, and one thing is where this thing that note that your that angle between this your what you call voltages, it will be difference should be 120 degree. This all we have seen, right. Vn is equal to VL upon root 3 is equal to Vp upon root 3 angle minus, in the delta case line voltage is equal to phase voltage, right. So similarly Van will be IaZy is equal to VL upon root 3 angle minus 30 degree is equal to Vp upon root 3 angle minus 30 degree. Similarly for Vbn and similarly for Vcn, right. So this is what we call that your this transformation of delta source to equivalent star source. Just show you that how one can do it, right. So next you take one small example, that a balanced star connected load with a phase impedance 40 plus j 25 ohm is supplied by a balanced positive sequence delta connected source. When you say positive sequence delta connected source means it will be, you take ABC sequence, right. With a line voltage of 210 volt it is given, you calculate the phase current, use VAB as reference phasor, right. So ZY, that star connected it is, so Z star or ZY is given 40 plus j 25 is equal to 47.17 angle 32 degree ohm, and VAB is the reference voltage. So here it is your with a line voltage of your line voltage means it is a line to line voltage, right. Whenever you say line voltage, it is line to line voltage. Whenever you say phase voltage, it is phase to neutral, right. So VAB is equal to 210 angle 0 degree. This is a reference we have to take. So we know, we have derived this, we know Ia is equal to VAB upon root 3 angle minus 30 degree by ZY. Just now we have derived this formula. So just go through this, right. So if you VAB is equal to 200 by 210, if you substitute VAB and ZY, you will get 2.57 angle minus 62 degree ampere. This is your ZY is given and VAB is also given. So you just simplify, it will get 2.57 angle minus 62 degree ampere. So now we know IB is equal to IA angle minus 120 degree. So this IA value 2.57 angle minus 62 degree, then you substitute here. If you substitute here, so it will be minus 62 minus 120 angle will be minus 182 degree, and this magnitude of the current will remain same 2.57 ampere. Similarly, IC also is equal to IA angle 120 degree. So here it will be IA is equal to 2.57 and angle minus 62 plus 120. So it will be 58 degree ampere, right. Next is a power in a balanced system. In a balanced system, now we begin by examining the instantaneous power absorbed by the load, right. So power in a balanced system. So for, because we have to see the three phase power also. For star connected load, the phase voltages are, this is actually VAN, let's say phase voltage VAN, we are making it capital AN, right, star connected load. So I mean it is your something like this. Suppose you have a we have seen already, I have made it for you before, right. This is a star connected load, right, this is a star connected load, and this is your capital A, say this is capital B, and this is C, and this is capital N, right. And that's why this is called VAN, this is your VAN, this is VBN, and this is VCN, right. And your phase voltage is VP, that is your magnitude of the phase voltage, that is RMS value, and multiplied by root 2 means it is the peak value, and representing it by the cosine term, sine, cosine, right. So cosine also you can convert it to your what you call sine 90 degree minus theta cos theta, right. So we are representing this as a cosine thing, right, say cosine one. So now let me clear it. So in this case, that means the earlier we have seen that your V is equal to, we have already seen, no, V, we have already seen for single phase AC circuit V is equal to Vm, let me clear it, V is equal to Vm, that sine of omega t. So, Vm is the peak value and Vm is equal to actually root 2 into V RMS value, that we have seen for single phase AC circuit. The same thing is here also, instead of sine we are represented by cosine, meaning is same, right. So, in this case this peak value is equal to then root 2 V. So, Vp is the your what you call, that is the phase voltage, but it is RMS value. So, multiplied by root 2 is peak value. So, next one will be, it will be omega t minus 120 degree, understandable, same as before, 3 phase system, and for VCN it will be root 2 Vp again cos omega t plus 120 degree, right. So, this is the representation of Van, Vbn and Vcn, right. It is written here Vp max is equal to root 2 Vp peak value, right. So, this is 120 degree apart, and Vp I have told you it is phase voltage, phase value, but it is RMS value, right. So, phase voltage RMS value, right. So, let me clear it. So, now angle, the current, sorry, the impedance Z y is equal to Z theta, say. So, the phase current lag behind the corresponding phase voltage by theta. So, this is my star impedance Z, your what you call your impedance of the star connected load. So, that is Z theta, it is Z angle theta, it is a balanced one. The phase current lag behind their corresponding phase voltage by theta. Thus, we can say Ia also we can write that root 2 Ip cos omega t minus theta. This is because current will lag by your voltage here. Voltage here it is omega t minus 120 degree, omega t plus 120 degree, and current will lag from this voltage. So, current also can be represented as Ia is equal to root 2 Ip. Ip is the your what you call RMS value of the current, that is your phase current, right. So, phase value. So, multiply by root 2. So, this is your peak value, right, and it is star connected. So, Ia is equal to root 2 Ip cos omega t minus theta, right. So, your what it is written here, Ip is the RMS value of the phase current, right. So, and Ib is equal to root 2 Ip cos omega t minus theta will be okay, minus 120 degree, because shifting by 120 degree, and Ic will be root 2 Ip cos omega t minus theta plus 120 degree. For voltages it was cos omega t minus 120 degree and omega t plus 120 degree, because the current lags by an angle theta. So, minus theta minus theta minus theta will be introduced here, right. This is understandable. Now, the total instantaneous power in the load is the sum of the instantaneous power in the 3 phases, right. So, all the 3 phases, right. So, if you do so, P is equal to Pa plus Pb plus Pc is equal to Van into Ia plus Vbn into Ib plus Vcn into Ic, right. I mean circuit wise, if you draw like this, it will be something like this. Suppose this is your star connected, this is your star connected, right, load, it is star connected. So, this is your N, this is your A, suppose this is your B, this is your C, this current is say Ia, right, this current is say Ib, and this current is say Ic, right. So, this here then it will be Van for this phase into Ia. Similarly, for this phase it will be Vbn into Ib, for this phase it will be Vcn into your what you call the Ic. This point is N, right. So, that's why we are making it Van into Ia plus Vbn into Ib plus Vcn into Ic, right. I mean all each phase, and if you substitute your Ia, Ib, Ic, and from here your Vn, Vbn and Vcn, if you substitute and simplify, please do this, right. So, such that if you do this, it will be in this form, P is equal to 2 Vp Ip, then cos omega t minus theta plus cos omega t minus 120 degree into cos omega t minus theta minus 120 degree plus cos omega t plus 120 degree into cos omega t minus theta plus 120 degree. You simplify this. I have written the final one, but you simplify this, right. So, I mean in your class 11 mathematics trigonometry formula, you use this formula like this, cos A cos B is equal to half cos A plus B plus cos A minus B, and simplify. If you do so, it will become P is equal to 3 Vp Ip cos theta, right. So, thus the total instantaneous power in a balanced three phase system is constant. That means it is time invariant, it is not a function of time, right. So, it is time invariant. So, system is constant, it does not change with time as the instantaneous power of each phase does. For the instantaneous power for your what you call each phase, it is okay that as the for each phase it does, but for three phase if you make it together, it will be 3 Vp Ip cos theta. So, it is independent of time, right. This is one of the main advantages of three phase using three phase system, right. So, the results is true whether the load is a star or delta, whether star or delta, this 3 Vp Ip cos theta is true, right. So, this is one important reason for using three phase system to generate and distribute power, because of your power is your what you call independent of the time. So, that means since the total instantaneous power is independent of time, I told you the average power per phase Pp for either delta connected load or the star connected load will be P by 3, because it is a balanced system, it is a balanced system. Therefore, Pp is equal to then per phase power will be P by 3, P was 3 Vp Ip cos theta. So, Pp will be Vp Ip cos theta per phase, right. And similarly, and the reactive power per phase will be Qp is equal to Vp Ip sin theta, right. So, the apparent power per phase will be Sp will be equal to Vp into Ip, right. So, no multiplier of cos theta sin theta, simply will be Vp into Ip. So, the complex power per phase will be Pp plus jQp is equal to Vp Ip conjugate. This thing has been explained also for single phase, right. So, meaning is very simple. So, total average power will be then Pa plus Pb plus Pc is equal to 3 Pp. So, it will be 3 Vp Ip cos theta, right. But this can be written as root 3 VLIL cos theta. Look, for a star connected load, line current is equal to phase current. When you will solve numericals, this thing should always remain in your mind, right. So, for a star connected load, line, I told you earlier, line current is equal to phase current, but your line voltage, right, line voltage will be root 3 times phase voltage. The meaning is, once again I am telling, suppose this is your star connected load, right. Suppose this is your star connected load, this is your star connected load, right. So, in this case, this is my line current, this is my line current, same current is going to this phase. So, this is my phase current. So, line current is equal to phase current, this way I am telling you, and this point is your N, right, this point is your N, and this is your what you call, say this is my VAB and C. So, my VAN, actually this here you make small n for your understanding, so it is small n. So, VAN is this point, this is my phase voltage, but your what you call, but line to that is your what you call, that Vp is equal to, say all balance it is. So, it is VAN is equal to VBN is equal to VCN magnitude, right. So, Vp is equal to VAN, but line to line voltage is this one, say this is my VAB, right. So, magnitude of VAB, right, is equal to then root 3 times your phase voltage, that is root 3 times VAN, but VAN is equal to Vp. So, it will be root 3 times Vp. So, line voltage is equal to root 3 times phase voltage. So, let me clear it. So, that's why for a star connected load, that's why this one it can be written as your IL is equal to IP and VL is equal to, that means it is actually 3 Vp Ip cos theta. This can be written as root 3, then in bracket you write your root 3 your what you call Vp, right, into Ip, then cos theta. So, root 3 will be there, and root 3 Vp is equal to your line voltage, it is VL, and Ip is equal to IL, right, because phase current is equal to line current. For your star connected load, then it will be IL, then cos theta. So, this term is written like this. So, it is root 3 VLIL cos theta, right. So, this is for a star connected load. Similarly, for a delta connected load, just opposite. So, no need to explain again, similar way you can do it. Line current is equal to root 3 times phase current, but VL is equal to Vp. Anyway, just let me make it for you. So, this is my delta connected load, this is my delta connected load, right. and this is phase A, phase B, phase C. Suppose this is A, this is B, this is C, right? No neutral is end point is involved here. So this is balanced. So this is my your say line current, and as per magnitude wise, this is my phase current. So this is my IP magnitude wise, right? And in that case, here line voltage is equal to phase voltage, or what you call line voltage is equal to phase voltage. For example, if it is VAN, that is the voltage across this one only, it is also delta connected load. So line voltage B, or what you call, this is my VAB, this is my VAB is equal to, basically this is also voltage across, this is phase voltage same as the line voltage. So it is VAB is equal to VP, say magnitude. Similarly for VBC, VCA, all are VP, phase voltage. But here the line, here the phase current is here, and this is line current. So line current will be equal to root 3 times phase current. This we have seen earlier also. So similar way, that means similar way for delta connected load also, just IL should be root 3 IP and VL should be equal to VP, line voltage is equal to phase voltage. This you have to keep it in your mind from the your what you call from numerical point of view, right. Similarly, total reactive power is Q is equal to root 3 VLIL sin theta. So total complex power, it will be 3 phase, right. So per phase power is PP plus J QP, so multiplied by 3. So 3 PP plus J your QP, sorry 3 into PP plus J QP is equal to this one, PP plus J QP is equal to, we can write VP IP conjugate we have seen. So it will be 3 VP and IP will be is equal to VP upon ZP whole conjugate. So that means 3 VP conjugate upon ZP conjugate. So VP into VP conjugate will be magnitude VP square, because if VP, suppose if VP is equal to VP angle theta, for example say, then VP conjugate will be VP angle minus theta. So if you multiply this, it will be VP and VP square magnitude, and it is theta minus theta, the angle will be 0. So it is just a VP square, that is why it is VP square, 3 VP square, and this whole thing is conjugate. So VP conjugate is here divided by ZP conjugate. So this is ZP conjugate, right. And ZP is equal to your what you call ZP angle theta. So if ZP is equal to ZP angle theta, then ZP conjugate will be ZP angle minus theta. This is magnitude, right. Sometimes we write like this, but it is understandable to you, right. It is, rather than putting bar, not do it, but this is magnitude, this is angle, understandable to you, right. So now right, so the impedance per phase, so ZP Z phase is equal to ZY, or ZP, this is ZP actually, ZP is equal to Z delta. So this is 3 VP square upon ZP your conjugate, right. So now we can write now then P plus JQ. So we also can write P plus JQ equal root 3 VLIL angle theta. Then if you make it, it will be root 3 VLIL cos theta plus J root 3 VLIL sin theta. Therefore P is equal to root 3 VLIL cos theta and Q is equal to root 3 VLIL sin theta. So we can write like this also, right. So now another thing is that a second major advantage of 3-phase systems for power distribution is that the 3-phase system uses a lesser amount of wire, right. So 3-phase system uses a lesser amount of wire than the single phase system for the same line voltage VL and the same absorbed power PL, right. So this is your what you call that another major advantage. Now how we will do this? We have to compare. For example, suppose we will compare these cases and assume in both that the wires are in the same material. In both the cases, single phase or 3-phase, we assume that wires are of same material, right. Therefore, suppose if you take a single phase source, and suppose this is incoming path and this is return path, so resistance is R and R, so it will be 2R, right, and this is the load connected. For the sake of our calculations or easy calculations, or for the sake of explanation, this load is a purely resistive load, right. This is a purely resistive load. If load is purely resistive, means it is unity power factor load, because Z is equal to say R plus JX. If X is equal to 0, then it is a purely resistive load, and across the load the voltage is say VL, that is the load voltage. Across the load this voltage is VL, right. So this is 2-wire single phase system. This is incoming path, this is return path, and the resistance here is R, same wire, so here is R and same length. So this is figure 22, right. Now Now this one, your if for 3-phase system we assume also same thing, that your 3-phase system. So resistance is R dash R dash R dash, 3 lines is there, phase A B C. This side is 3-phase balance source, right, and this is 3-phase balance load. And here also we are assuming it is a, for each, whether it is a star or delta does not matter, we assume a pure resistive load. So power factor of the load is unity, right. And here also your what you call voltage across the your what you call that VAB, that is this side is VAB, this is R dash is there, some voltage drop will be there, but across there the phase your what you call line to line voltage across this load, this is VL angle 0 degree, and this is say B to C, it is VL angle minus 120 degree. When we are writing that plus minus, it is instantaneous polarity. That means my VAB is equal to VL angle 0 degree and VBC is equal to VL angle minus 120 degree. This is whatever written here. This is A to B. So this is basically line, this line. So basically it is your what you call, if this is this we can write, if we ignore this loss in this line, right, then this VAB is equal to VL angle 0 is equal to VBC. But as the current is flowing, this is my IA, so there will be voltage drop here. So this one, whatever VL will be, it will be slightly less than AB, right. So anyway, so in this case your what you call, in this case VAB or VBC, their magnitude not exactly equal to the your what you call the VL, because this some drop is voltage drop will be there in this R in the resistances, right. But anyway, nothing to bother about that. We will show that the 3-phase your what you call takes less material than the your single phase. So now for the 2-wire single phase system, that is figure this, from this figure it will be IL is equal to simply VL, right, PL upon VL. So it is a resistive load. If power is the PL resistive load, then IL will be simply PL upon say VL, right. So your what you call, if it is your AC single phase AC system, so if you take VL angle 0 also, it will be VL only, right, and it is a resistive load, so no Q, so IL should be is equal to PL upon VL. Then the power, then the your what you call, this current is IL, then power loss will be IL square into 2R, because here it is R, here it is R, right. You substitute this one, you will get PL square into 2R upon VL. That is what has been done, right. That is what has been done here. So 2R into PL square, this is equation 1. Now for the 3-phase 3-wire system, IL dash will be magnitude IA, magnitude IB, magnitude IC is equal to your say PL upon root 3 VL, because your it is unity power factor load. So root 3 VL, we know that general root 3 VL, the current we have taken IL dash, because for single phase we have taken IL, that's why it is IL dash, right, cos theta is equal to your PL plus JQL, that is the formula, right. So sorry, so is equal to PL, right. So now question is that cos theta is equal to unity, because resistive load, right, it is a resistive load, therefore IL dash will be PL divided by root 3 VL, right. So now the power loss in the 3 wires will be IL dash square into 3 R dash, because 3 lines are there, so 3 R dash, so it will be 3 R dash into PL square upon 3 VL square. So 3 will be cancelled, it will be R dash into PL square upon VL square. So this is equation 2, right. Now if you divide equation 1 by equation 2, you will get P loss upon P loss dash is equal to say 2R upon R dash, right. You just do it, you will get it. Now we know that R is equal to, we use the same material, that wire is made of the same material for both the cases. So R is equal to capital R, that is the first case, that is single phase case, rho L upon pi R square. We are assuming that the radius of the conductor for the single phase is R, right. So it will be rho L upon pi R square. Similarly for the 3-phase case, R dash will be rho L upon pi R dash square, right. So they are of the same material and same length, right. So rho will remain same, and your what you call only radius will be different, say for the single phase it is R, and for the 3-phase radius is R dash square, right, R dash. So it is R is equal to this, R dash is equal to this. You substitute here, you substitute R and this r dash here you substitute. If you do and simplify, you will get P loss upon P loss dash is equal to 2 into r dash square divided by r square. This is equation 3, right. If both the what you call if the same power loss is tolerated for both the system, that is P loss is equal to P loss dash. If you do so, that means if you do so P loss is equal to P loss dash equation, then it will become r square is equal to 2 r dash square, right. So that means my r square upon r dash square is equal to 2. This is equation 4, right. Now that material for single phase by material for 3 phase, this is volume. So conductor, your conductor can be represented, that is a long wire is represented by a cylinder, right. So if length is L and the single phase case, if r is the radius, so pi r square L, right. So this is your what you call the volume, it is taking as a cylinder, right, because cross section is circular, divided by your material for the 3 phase case, it is 2 wire, it is a 2 wire system. So 2 into pi r square L, right, that is the for the single phase case, this is the volume, and for the material for 3 phase case, it is a 3 wire. So 3 into pi r dash square L, this is the volume. So if you simplify this, so pi will be cancelled, L will be cancelled, it will be 2 by 3 into r square by your r dash square. So r square by r dash square is equal to 2, so it will be 4 by 3 is equal to 1.333. That means material for single phase wire, that is volume actually, is equal to 1.333 into material for the 3 phase. That means if you use single phase for the same power loss, right, that your volume of the conductor is 33.3% more than the 3 phase, right. That is why 3 phase 3 wire is the benefit, what you call more beneficial. So this is the idea. So now take one example, but I mean for example, you please see the example 2, same example 2, you just see, you have to determine the total average power, reactive power and complex power at the source and at the load, right. So if you, I mean I am not going to the example 2, but just go back to that example 2. So in this case what happened, the system is balanced and it is sufficient to consider single phase, right. So system is balanced, so single phase analysis is sufficient. So for phase A, phase voltage is equal to Vn at 110 angle, this is given, and this IP phase current also is line current, we have also computed 6.81 angle minus 21.8, there we have computed all these things, right. Now at the source, so SS is equal to, that is S suffix S small s stands for source, is equal to 3 Vp Ip conjugate, because 3 phase system Vp Ip conjugate into 3. So if you do so, this is my Vp and this is Ip conjugate, right. Ip is 6.81, so Ip conjugate will be 6.81 angle 21.8 degree, right. So it will be 3 Vp Ip conjugate will be 2087 plus j 34.6 volt ampere. Look, whenever you are making it, this is my watt, this is actually my watt, right, and this is my var, right. So basically when we write in this form watt plus your var, this can be as volt ampere. For example, suppose if you write P is equal to say 30 watt and Q is equal to your 20 var, right, it is okay, but when you write in this form P plus JQ 30 plus J20, it will be volt ampere. That is why this together, when you write this in form, I mean P plus JQ form, it will be volt ampere, right. But this one is watt and this one is var, because if you take its magnitude, it will be volt ampere. That is why we write VA. So in this case, the real power supplied is that 2087 watt and the reactive power is 834.6 var, right. Now you see that example 2, it's very data, everything is given. So at the load, the complex power absorbed is, so S load is equal to 3 Ip square into Zp, it is a balanced system. So Ip square Zp is per phase into 3, right. So this way you can write. So Zp is given 10 plus j8 ohm, that is 12.81 angle 38.66 degree, right. Therefore it is 3 into 6 point, current magnitude is 6.81, so 3 into 6.81 square into 10 plus j8, right. So this is your volt ampere. So this you can write S load is equal to your 1398 plus j 1113 volt ampere, right. So, in this case the real power absorbed is 1392 watt and reactive power is 1113 var, and total if you make it will be volt ampere. This is what? This is var, I told you. So, the difference between the two complex power is the power absorbed by the line impedance, that is the power loss, right. So, power absorbed by the line is, it is 3 into current square, right, magnitude 6.81 square, and line impedance is 5 minus J2. So, it is coming 695.6 minus J to 278.3. So, when it is minus means it is capacitive, right, it is capacitive, like your what we call impedance is capacitive. So, this real power absorbed by line 695.6 watt, that means this one, and reactive power absorbed by line is minus 278.3 var, right. Now, next is unbalanced 3-phase system, just one or two, just half page I will tell you. Suppose this load, suppose is the unbalanced can be anything, ZA, ZB, ZC, it may be different, right, its magnitude may be different, angle may be different. Similarly, supply voltage, your VAB, BC, CA, right, all these things may be different. I mean, if your one is different slightly, then it is unbalanced system. So, in the case of unbalanced system, IA is equal to say current here, this current is your what you call this current, this is IA current. So, this current is IA, right. So, it is going to this phase IA. Similarly, for your this thing IB, right, and similarly for here it is IC, right, and this is that neutral point N, and this is ZA, ZB, ZC, and this phase voltage VAN, VBN and VCN. So, unbalanced system phase voltage also may be unbalanced. So, IA is equal to VAN by ZA, IB is equal to VBN by ZB, and this is star connected load, and this is star connected load. So, IC is equal to VCN by ZC. Now, if you apply KCL here, right, so it will be your IN plus IA plus IB plus IC is equal to 0. That means, my IN is equal to your minus IA minus IB minus IC, that is what I have written here, right. If you put it in bracket, so it will be this thing minus of IA plus IB plus IC, and in that case if it is unbalanced, this IN may not be 0, right. So, let me clear it. So, that is all for little bit idea for unbalanced system, right. Okay, thank you very much, we will back again.